Buckle up, everybody, because today we are diving headfirst into theoretical particle physics.
Ooh, exciting.
We've got this paper, right? It's called Landscaping CP-Violating BSM Scenarios.
Okay.
And it's tackling this question that has been puzzling physicists, honestly, for decades, which is, why does the universe seem to prefer matter over antimatter?
Yeah, it's a really good question to highlight some of the gaps in what we think we know about the universe.
Right.
We have this thing called the standard model of particle physics.
Right.
And despite the impressive name, it kind of fumbles when it comes to explaining this whole imbalance between matter and antimatter.
It's like the universe had this giant game of cosmic dodgeball, and
Okay.
somehow all the antimatter players got knocked out way too early.
Yeah.
But this paper, though, it's not just some theoretical mind game. This is actually designed to guide some of the experiments happening at the Large Hadron Collider, that giant atom smasher that we all know and love. And it's really cool to see how theorists can influence these, like, massive, massive experiments.
Yeah, absolutely.
Yeah.
This paper focuses on this really clever tool called effective field theory, or EFT.
Okay.
And you can imagine trying to study a star. You can't really touch it,
Right.
but you can study the light that it emits.
Exactly, yeah.
EFT is kind of like that, but for particle physics.
Oh, okay.
So it lets us look for clues of new particles, new forces, even if they're way too big, way too massive for us to create in our experiments directly.
Okay, so how does this help us understand CP violation, this EFT thing, and what was it you were saying about cosmic dodgeball?
So CP violation, at its heart, it's all about symmetry,
Okay.
or really the universe's lack of it.
Okay.
So picture this, right? You have a mirror and a video camera.
Okay.
You record the universe doing its thing running along.
Okay.
And then you play the video back in reverse on the camera while also looking at it in the mirror.
Okay, so everything's flipped.
Everything's flipped. So if the laws of physics were perfectly symmetrical, this mirror image universe, where everything is flipped in terms of charge, C, and parity, P, should behave exactly the same way. That's CP symmetry.
Okay. So something off, though.
Something is off. It's like the universe looked at that mirrored video and was like, nah, I'm going to do my own thing.
Yeah.
And in reality, what we observe is this glaring preference for matter over antimatter.
Right.
And the standard model, it does explain some of this asymmetry,
Okay.
but not nearly enough to account for all this matter that we see around us.
Oh, wow.
And that's where beyond the standard model physics, BSM, comes in. So physicists are essentially trying to find the missing pieces of the puzzle.
Right.
Those new particles or forces that could explain why matter won this game of cosmic dodgeball.
So that's where these invisible elephants come in, these
Yeah.
like hypothetical particles that could really change how we view the standard model.
Yes, you got it. The paper looks at how these hypothetical, incredibly heavy particles might subtly interact with the particles we're already familiar with.
Okay.
And even if we can't detect these heavyweights yet, those interactions would leave behind telltale signs.
Right, like those dust disturbances that we were talking about.
Okay,
Yeah.
I'm hooked. Tell me more.
Yeah.
So how do we look for those dust disturbances using this EFT?
Well, you can think of EFT as like a translator
Okay.
between the extreme high energy realm where these new particles might live and the lower energies that we can actually create in experiments like at the LHC.
Right.
It helps us understand how those massive, massive particles might influence the behavior of the particles that we can see.
So we're looking at the influence of these really, really large particles, but not observing them directly.
Yeah, it's like detective work.
Yeah, exactly.
Exactly.
That's some serious detective work.
Yeah, and what the researchers are doing is they're focusing on a specific area of the standard model.
Called the gauge-Higgs sector.
Gauge-Higgs sector, okay.
And this sector, you can think about it as like the control room for all the fundamental forces and particles in the universe.
Okay, so it's important.
Yeah, it's a big deal. It's where we think those dust disturbances would be the most obvious.
Okay, so we're looking in the gauge-Higgs sector for these BSM effects, which could clue us into these massive hidden particles.
Yes.
Okay, this sounds really complicated.
It is.
Like we're looking for a specific grain of sand on a beach.
Yeah, and that's where landscaping comes in.
Oh, okay.
So you see, EFT can generate a ton of possible clues.
Okay.
Like a whole beach full of sand.
Right.
So these researchers are advocating for a more targeted approach
Okay.
to try to make sense of all the possible signals.
So landscaping the possibilities.
Yeah.
I like that.
It's less about this like blind search
Right?
and more about mapping out the terrain
Okay.
and finding the best places to look.
Very cool.
Right.
So how do they do that?
So they're exploring scenarios involving these hypothetical particles called, get ready, vector-like leptons, or VLLs.
Okay, hold on, hold on. I think we need a little bit of an explainer here.
Okay, sure.
What is a lepton, first of all?
So leptons are a type of fundamental particle,
Okay.
which means they're not made up of anything smaller,
Okay.
at least, as far as we know.
As far as we know.
And electrons, those tiny little particles that power our electronics,
Right.
are a type of lepton.
Okay, got it.
Yeah,
Electrons, the little guys.
the little guys.
So these VLLs, these are kind of like they're much heavier hypothetical cousins.
Yes, exactly.
Okay.
And the cool thing is these physicists think that these VLLs, they might interact with other particles
Okay.
in ways that could create those CP-violating effects we've been talking about.
Okay, so these VLLs interact with these known particles, and that could lead to these CP-violating effects.
Yes.
These dust disturbances. Okay, I think I'm following. But how do we actually see these interactions in the data? We're talking about things happening at a subatomic level.
Right. So what they do is they focus on very specific signs of CP violation.
Okay.
And these are represented by mathematical terms that they call operators.
Operators, like mathematical equations.
They're more like specific patterns of interaction between particles.
Okay.
You can think about it like a pool table, right?
Okay.
The operators describe the different ways that the billiard balls can collide and scatter.
Got it.
And the paper focuses on this one really interesting operator called QW tilde.
QW tilde, that sounds kind of mysterious.
It is kind of mysterious. And it's super rare. It only pops up in very specific situations involving these heavy VLLs.
So finding this rare QW tilde, this would be a big deal, right? This would be a major clue that these VLLs exist.
It would be a huge deal. It's like finding that one specific grain of sand on the beach that tells you, hey, there's buried treasure here.
That is a fantastic analogy. I love that. Okay, so where do we go from here? How do we even begin to search for these very subtle signals in this massive amount of data coming out of the LHC?
That's a great question. And these researchers, they came up with a really clever strategy. So they suggest we focus on two main events that are happening in the LHC.
Okay.
Events where we see a Higgs boson being produced, especially when it decays into those heavier tau leptons.
Okay.
And also events where we see pairs of force-carrying particles. These are called dibosons.
Okay, so we're trying to see these Higgs bosons and these dibosons, and we're looking for variations in how often they show up.
Yeah,
That might point us towards these heavy particles, this QW tilde operator.
exactly. And here's the really clever part. They think that by combining the data from both of those types of events, the Higgs bosons and the dibosons,
Okay.
we could get a much clearer signal. It's like if you're using two different magnifying glasses.
Right. 2 is always better than 1 when we're talking about clues.
Exactly.
So how do they even begin to do that? Combine those clues. I mean, we're talking about a crazy amount of data coming out of the LHC.
Oh, it's an insane amount of data. The LHE is a data factory.
Yeah.
But to handle this, they use simulations.
Okay.
So they create a picture of what those Higgs and diboson events would look like with and without the influence of these CP-violating operators, including our friend QW tilde.
Okay.
And then by comparing these simulations to the real LHC data,
Right.
they can look for statistically significant deviations.
Statistically significant deviations, that's science talk for aha
Yeah.
moments, right?
Exactly.
Yeah.
I mean, they're finding patterns that are so unlikely.
Right.
They can't just be random chance.
Okay.
And to do this, they use some really powerful statistical tools like chi-squared analysis
Right.
to see if the real LHC data matches what their simulations say.
So they're not just looking for any old anomaly. They're really setting a high bar to make sure that these aha moments are really something.
Yeah, they want to be really sure. And the really great thing about this approach, focusing on specific signals, combining data from multiple sources, is it makes the search a lot more efficient, a lot more streamlined.
Okay.
It's like they're fine-tuning a giant superpowered microscope
Yeah,
to bring those tiny CP-violating effects into focus.
that's incredible. But what if, after all this searching, they don't find evidence for this QW tilde? Does that mean that it's back to the drawing board for these theorists?
That's the million-dollar question.
Yeah.
But the funny thing about science is even a no can be a big step forward.
So even a no can actually be a win for science. That's a really interesting way to think about it.
It's true. It's true. In this case, like if the LHC doesn't find this QW tilde, It doesn't necessarily mean that those BSM scenarios, those ideas are wrong.
Mm.
It means we need to refine our search a little bit.
So back to the drawing board, but at least now we know where not to look, maybe.
Exactly. Exactly. It's like our treasure map just got a whole lot more interesting.
Yeah.
We might need to look for a different kind of treasure chest, or maybe the treasure's buried even deeper than we thought.
Ooh, okay. So what happens next? What could these alternative explanations even look like?
Well, there could be other particles out there, right? Even heavier than those VLLs that might be contributing to these CP-violating effects.
Okay.
Particles we haven't even dreamt up yet.
Right.
Or it could be that maybe our understanding of the Higgs boson needs a little tweaking, or even like the fundamental forces themselves.
Right. Right.
We might need to make some adjustments there.
So it's like the universe is kind of like this onion, right? All these layers, and every time we think we're getting close to the center, we peel back another layer and there's like a whole new set of questions.
It's so true.
Yeah.
It's like that's the beauty of science.
Right.
It's like it's always a journey. We're always exploring. And this paper, it's just one step,
Yeah.
in this grand quest to try to understand the universe. Like, why are we even here?
When you put it like that, it makes this whole CP violation thing seem really profound.
It is.
It's not just about particles, it's about like our very existence.
Exactly. And it really shows you how important these big, these ambitious experiments like the LHC really are.
Right.
They're not just smashing atoms together. They're helping us answer some of the biggest, most fundamental questions that we can ask as humans.
This deep dive has been incredible. We've gone from what seems like a simple question, why is there more matter than antimatter,
Right.
to like hidden particles and, I don't know, multiple dimensions, the nature of reality.
The very fabric of reality.
What a ride.
It's pretty wild.
If you are as fascinated by this as we are, listeners, be sure to check out the show notes. We'll have a link to the research paper there if you want to dive even deeper. Let us know what you think. We always love to hear from you.
Yeah. Keep those brains buzzing.
Until next time, keep those brains buzzing and keep those questions coming.